Okay. So I finally got around to posting my office hours. I apologize. I had to update because I have to stick a seminar in the time on Thursday when I was originally going to have office hours. So right now, I think I've got Tuesday 1 to 2, Thursday 12:30 to 1:30, and then Friday 11 to 1. I will, if that doesn't work for you, I'll have appointments in other places we can do this. Because there's so much competition for that room under the breezeway, and because the library tent has so many whiteboards, I was thinking about just moving them back over there this quarter so people don't have to fight for seats. So we'll go to the library tent for this. So after my second section today, I'll just head right over there. If you have not yet visited the beautiful library tent, it's just in the parking lot right over there, the big white tent. Yeah. Is there one down that way? There used to be tents down in the engineering, west parking lots, but I think they got rid of those. So it's just the one right across the way between 38 and building 10. As the virtue, like I said, of tons of available seats. Okay. So, the chapter that we're going to work on today is 14.6, which is about the directional derivative. And the gradient. So I mentioned last time the motivation for the directional derivative was if you have some point A, B, so say you've got a function f taking a domain in 2 variables into 1, and you're at some point A, B, so all I mean by this is z is equal to f of x and y, that we had a derivative that pointed in this direction, which was fx at AB, and we had a derivative that pointed this way, which is fy at AB. So imagine some surface floating over the top of this, but those aren't the only directions we necessarily want to know how the function is behaving. I might want to pick an arbitrary direction. So what happens if I want to go this way? And the easiest way to sort of set up what we're asking for here is actually just to use the definition of the derivative to do it. So in one variable, f prime at a point x is equal to the limit as t goes to 0 of f of x plus t minus f of x divided by t. It's like this classic definition of a derivative. I'm going to modify that slightly because there's actually a calculation here that we don't show you when we write this definition down. This is really the limit as t goes to 0 of f of x plus t minus f of x over x plus t minus x. And normally we just cancel the x's out and don't show them to you, but that's what's really down there, right? And the point is that this guy right here measures the distance from x plus t to x. That's what that term does. How far away is x plus t from this point you began at x? And so we're going to use this notion to set up our idea of a directional derivative. And the easiest way to get started is to say, well, if you had f of x and y, and you wanted to calculate the way that we actually define the partial derivative of f, I presume that Dr. Champney did this. If we wrote down fx at a point x naught, y naught, the definition of that was the limit as t goes to 0 of f of x naught plus t, comma, y naught minus f of x naught, y naught over t. Right, so it's like you slide out a little bit in the x variable and just take a one variable derivative that way. And likewise, fy at a point x naught, y naught is the limit as t goes to 0 of f of x naught. Okay, well now don't move in the x direction, move in the y direction. Y naught plus t minus f of x naught y naught divided by t. So it's like a one variable derivative where now we're moving in the y variable instead of the x variable. So the easiest way to think about how to set up a derivative in a different direction is instead of moving in the direction of the vector 1, 0, which is how you moved here, or the vector 0, 1, which is how you moved here, we're going to assume that this vector has coordinates like a, b, and we'll move in both the x and y variables simultaneously. It's not this terrible eraser. So we're going to start by assuming, and I'll explain why in a second. So we're going to assume that we have a vector u, which has coordinates a, b, and we're going to assume that this is a unit vector. We'll talk about why in a second. And now, instead of moving in the x direction or the y direction, I can take a limit as t goes to 0 of f of x naught plus ta y naught plus tb minus f of x naught y naught all divided by t. So essentially what we're doing now is we're saying instead of moving in the x direction or the y direction, move in a combination. Move towards the vector ab. The picture of what's happening here is if you have some point x naught y naught, we are now moving in the direction of a vector u, which is ab. And what the t is a scaling factor. So as t goes to 0, essentially what we're doing is we're starting at some point on the line determined by that vector, and we're sliding back into the point as t goes to 0. So it's just a regular old derivative calculation. Okay. Now the reason that this is a unit, I guess before we go on here, it's annoying to write this down and just say a directional derivative in the direction u, so we give it a name. The symbol stands for this, and in Stewart's book, that symbol is capital D, the derivative in the direction u of the function f at the point x naught y naught. Here's a mouthful. And we call this the directional derivative of f in the direction u at the point x naught y naught. Okay, so why a unit vector? So the actual theorem here, if you wrote this out where slope is equal to rise over run, you have to account for the length of the vector that you're computing over the top of. And so in the original formulation for the derivative, this was really a distance between 2 points, right? How far we went from this one to that one. And so one way of thinking about this expression is, this is like x plus t times the number 1 minus x. So this is basically a scalar vector 1. So this is a unit vector here. And what we're doing is we're saying, okay, how long is the distance between those things? It's t. T scales us back down. If you do the subtraction, you get t times 1. T times something of length 1. It's essentially identifying that the run of our slope, remember slope is rise over run, is of length 1, which means the number that comes out will just be the rise. I don't have to adjust it at all. So over here, technically, if this was not a unit vector, there would be a length of the vector u right here. I can actually set this up for any vector I want. But if it's length 1, then that term just vanishes. And so why not just assume the vector is a unit vector? Right? And essentially, this is, if you want to think about it, this is like the run in a slope calculation. So we're just assuming that the run is equal to 1 so that whatever the number comes out is the rise. Yep.
So any vector you have, just make it into the
Yeah. So generally when you're computing a directional derivative in practice, you just pre-take your direction, make sure it's a unit vector when you do the calculation. So these things are kind of annoying to do by the definition, so let's do an example of that before we come up with our calculation formula. Just like with derivatives, it would be sort of obnoxious if I say, oh, f of x and y is equal to x squared y, and I'm going to calculate duf at the point 2, 1 in the direction, right, in the direction u, where u, say, is the vector 1, 1. Yep. Oh, sorry, wrong class. This is a point because you're evaluating it. This is a vector. Oh yeah, it's supposed to be z is equal to f of x and y. I got 2 of these classes that are basically the same but at different levels, and it's hard to keep them straight in my head sometimes. Yeah, so there you go. I think that's a z is equal to f of x and y because just a scalar comes out, so it makes sense to compute a directional derivative. So if this is all we had to work with, then I have to write down, well, I guess the first thing is u is not a unit vector. That's obnoxious. So this is not a unit vector. So probably the first thing I should do is I should write a vector v down. So v is the vector 1, 1 divided by the length of 1, 1, which is 1 over root 2, comma 1 over root 2. Already yucky. And now if you want to calculate this thing, you have to write down the limit as t goes to 0 of f of 2 plus t times 1 over root 2, comma 1 plus t times 1 over root 2 minus f of 2, 1, all divided by t. And you think to yourself, my God, there's going to be a lot of crap going on there. This is just the formula for the derivative, right? This is literally this. The x naught, y naught here is the 0.21. The a and the b are the 1 over root 2 and the 1 over root 2. I have to calculate this limit. Sure, it'd be nice if there was a computational formula, so I didn't just have to immediately start doing these kind of limit calculations. What is this even? Oh, it's going to be so bad. 2 plus 1 over root 2 t all squared plus 1 over root 2 t. That's this function. Minus f of 2, 1. Well, that's 5. That's easy. All divided by t. And then take a limit as t goes to 0. And already probably you're thinking, like, there's got to be a better way to do this. We don't calculate derivatives wouldn't be useful if I had to calculate them from the derivative or from the definition every single time. I think this ends up working though. I guess if we're feeling masochistic, we could just continue our calculation. It's like a cup of coffee in the morning, calculating some ridiculous derivative. 2 squared is 4, and I'm going to get 4 over root 2t plus, there's going to be a 1/2 of a t squared minus a 5. Oh, sorry, 2 squared. Oh, I forgot something. I forgot this, right? Plus 1 over root 2t minus 5 all divided by t. And then, if you remember your original calculation of derivatives, all the things without t's should cancel or you're not doing it correctly. So the 4 and the 1 get eaten by the -5. And now you're left with, also there's t's all over the place. So this t down here cancels that t and this one, and then that t drops to a first power. And so when you're done calculating this, I think you end up with 4 over root 2. I forgot to calculate this t. That also, okay. No, that one vanishes because you put in the then t is equal to 0. So is it just 4 over root 2 plus 1 over root 2? Which is 5 over root 2. Calculate the limit. Okay, there you go. We painstakingly ground out 5 over root 2. Man, that's awful. Okay, so the thing to notice here is that we can actually use the gradient to do this. And the reason we can use the gradient to compute these things isn't totally obvious from a computational standpoint. But from a vector standpoint, it seems reasonable to believe that maybe because we have tangent planes involved, maybe it's the case that if I'm at some point x naught, y naught, and I know the derivative in this direction, which was fx at x naught, y naught, and I know the derivative in this direction, which was fy at x naught, y naught, maybe I can figure out the derivative in this direction as a combination of these two slopes. That would be the ideal thing to be able to do, because the gradient is really, sorry, these fx and fy are really easy to compute, really easy. Because we can just use our standard theory to do that. And so it turns out this is our sort of first big theorem here. If u is a unit vector, then the directional derivative of f in the direction u is equal to fx, fy dotted with ab. Let's say u is equal to ab. That's quite a bit easier. That says I don't need to do anything with limits. I can just calculate some partial derivatives and take a dot product. So let's actually verify that we get the right thing when we do it here. See if you can test how good my math is early in the morning like this. So according to this theorem, instead of grinding that all the way out there, what I could have done is calculate fx, which is 2x, and fy, which is 1. And then fx at the point 2, 1 is equal to 4, and fy at the point 2, 1 is equal to 1. And then the claim of the theorem is that the derivative of f in the direction u is equal to fx, which was 4, and fy at that point, which is 1, dotted with the vector, the unit vector, 1 over root 2, 1 over root 2, which is 4 over root 2 plus 1 over root 2, which is 5 over root 2. And that's really the way you want to do this, is like this way. Right? And this is a massive improvement in how we study the geometry of these functions, because it means that I can study all possible directional behavior by this really magical one. All the other directions are determined by that. Okay, so this thing, we give a name. I talked about this last time. That vector is so special and determines so much about functions. Fx, fy is the gradient of f. One of the most important pieces of information that you can extract from a function is its gradient vector. And we can call it nabla f, or del f, or grad f. Those are all names from different fields. I'll just say grad f. In some books, you actually might see this written as grad f. Means the same thing. And that's just the vector of partial derivatives. So another way of writing this directional derivative theorem, if I have this symbol that means take the vector of first partial derivatives, another way to write this theorem is that duf at a point x naught, y naught is equal to the gradient of f at that point dotted with the vector u. And that's the sort of way that you see this written in textbooks on engineering and physics, is this formulation. The math book is trying to ease you into the notation a little bit. Okay, now, in a regular class, some professors just declare this to be the definition. But we're burly in here, right? So I'm gonna show you why this works, because it's a way of seeing how the vectors interact with the functions, right? What the power of thinking about these things as vectors actually is. And there's one thing that we're going to have to assume as what mathematicians call a black box. So we're kind of going out of order because we did 14.3, 14.4. We're talking about 14.6 right now. And we're going to wrap back around to 14.5 because the ideas are kind of different. But there is one idea from 14.5 that we need. 14.5 is on the chain rule. And so I'm going to ask you guys to accept as a black box one assertion. And then we'll prove that our definition of the directional derivative is equal to this. Because there's no reason to believe this should be true except I demonstrated it to you. Right? One example shouldn't convince you that this is intrinsic. So here's your black box. If you have a function g of h, which is equal to f of x of h, y of h. That is, if I have a function f, so if I have a function g that's a composition of a function f with functions x and y, this is the setup for a chain rule is compositions, right? So compositions are more complicated in two variables. Then g prime of h is equal to df dx dx dh plus df dy dh. We're going to show why that's true when we do 14.5. For now, I just want you to think the reason that there's extra terms in the chain rule is because there's a function sitting in each slot of f. And so each slot of f is going to require its own derivative. F is a function of x, but it's also a function of y. And both x and y are functions of the independent variable h. So for now, I want you to take this on faith that this is true. If I covered this up, it would just look like the regular old chain rule from the earlier versions of calculus, right? So this is just what happens when you generalize it to functions of two variables. There's one place where I'm going to use that idea in this argument. Okay, so why is this true? So we're going to define a function g of h, just like this setup right here, to be equal to f of x naught plus ha, comma, y naught plus hb. Okay? So in particular, g of 0, so this is despite the setup here, this is a function that eats one input variable and produces one output variable, right? The h goes into f, f gets evaluated into a number. This is just a one variable function. One in, one out. What is g of 0? You replace the h's with zeros and you get f of x naught, y naught. Okay, that's good. So, what is g prime of 0? G prime of 0, if I was going to calculate that from the definition, g prime of 0 would be equal to f of x naught, let's see, what do you actually get when you do that? G prime of 0 is supposed to be equal to the limit as t goes to 0 of g of 0 plus t minus g of 0 over t. That's just the definition of the derivative, right? I'm not doing any calculation. I just literally wrote down the definition of the derivative. But what is g of 0 plus t? Well, that says everywhere you see an h in this formula, put a 0 plus t. The limit as t goes to 0 of, okay, so if there's a t here, don't we get f of x naught plus ta comma y naught plus tb? All I'm doing is I'm swapping h's for t's. Right? Because g of h is equal to this formula, so g of t is this formula with t's instead of h's. G of 0 is f of x naught y naught. And I take all that and divide by t, and it's like mathematicians pull this trick all the time, right? We make some fancy definition and it turns out to be exactly what we want, because isn't that just the definition of the directional derivative of f? This is just duf at x naught y naught. So I set this up specifically so that when I took its derivative, that would come out. Okay, so now what I want to show is that also g prime of 0 is equal to that dot product formulation. So I want to show, WTS means want to show, that also g prime at 0 is equal to fx, fy dotted with ab. Because if it's equal to this and it's also equal to that, then those guys are equal to each other, and we've demonstrated the formula. Okay, so now we get to use the chain rule. If g of h is equal to f of x naught plus ha comma y naught plus hb, then this chain rule says that g prime of h should be equal to fx at x naught plus ha, y naught plus hb. That's the derivative of f with respect to x, times dx dh. What's the derivative of this with respect to h? Just this bit right here. X naught plus ha, if I take its h derivative, I get a. Plus fy of x naught plus hb, comma y naught plus hb. That's the y derivative of f times the h derivative of this variable right here, that function, which is b. So what happens when I put in h is equal to 0? G prime of 0 says take all the h's and put zeros in. Fx, x naught, y naught, a, plus fy, x naught, y naught, b. The h's get destroyed, and you end up with fx, fy, dotted with ab. And that's the exact formula that we were after. So this kind of trick of setting up a function and pushing stuff into it is pretty typical in this kind of math. So it's worth seeing this because otherwise, when you do this chapter in the book, these things are just asserted to you. These are true, right? These formulas are true. But there's more going on here than just somebody asserting something is true. This is a natural property of the way that the derivatives are defined and set up. So, do you need to know this derivation? No, but you should know that you can get this, right? That the vector formulation of this is a really natural thing that you extract from the definition. And why are we done? Because on the one hand, g prime of 0 is equal to this. which is the gradient of f dotted with u. And on the other hand, g prime of 0 is equal to this, which is the directional derivative. And so they're equal to each other. Okay, that is probably the most technical thing we'll see for at least a week. So there you go. If you survive that, now we can just compute some examples. All right, so what do you actually need to know? What do you need to take away from this? You need to know just that calculation formula. duf is equal to grad f dot u Okay, so the next thing I want to talk about is properties of the gradient vector. So the gradient vector is a powerful object. So if I write down something like z is equal to f of x and y, which is equal to x squared y plus 3x y to the fourth, it's very easy to compute a gradient vector. So I can compute the gradient of f is fx, fy, which is 2xy plus 3y to the fourth, I think. And in the second slot, the partial with respect to y is x squared plus 12xy to the third. So there's a really easy set of computations that go along with producing these things, but the power of the gradient vector is actually what it means geometrically. So the gradient has a ridiculous set of properties. In fact, probably the most powerful numerical method currently in use is called gradient descent. And gradient descent, which is one of the core algorithms of machine learning, for example, is production of gradient vectors and then using them. So the properties of the gradient vector, you should see why we use them in a second here. So here's properties. Properties of the gradient. So 1, the gradient of f points in the direction of steepest increase. Of z is equal to f of x and y. So if you're hiking a mountain and for some reason you were carrying around the function of the mountain, you could stop where you were, figure out your coordinates, calculate your gradient vector, and that would tell you what direction to go up the hill as fast as possible. 2, the length of the gradient vector is the slope in the steepest direction. So that is to say, the direction tells you how to head if you want to increase as much as possible, and the magnitude of the vector tells you how much you'll go if you go that direction. So for example, if I was trying to climb, if I had some function that was describing some economic or scientific problem, and I wanted to know how to find the maximum value of my function, one strategy I could use to do that would be to say, like, if I didn't, say I didn't have eyes or something, or like somebody put a blindfold on me, and I was climbing a mountain, and I wanted to get to the top, but I somehow had a calculator that could tell me the gradient in any direction. I want to climb to the top of the mountain. I'm at a point xy. I calculate the gradient. I point myself that direction. Then I travel that way. I calculate a gradient. I turn in that direction, and I keep doing that, right? So I go in the direction of the gradient. I calculate a new one, and I keep going. You will eventually end up close to at least a local maximum of the function that you're working with. So this is a core set of geometric ideas that goes into what's called optimization. Finding local maxes and mins, yep. So the method that you use to do that is called the Euler's method, and how small the increments are is something that comes from whatever problem you happen to be studying. So the size of how far you're willing to move depends on how much computational power is available to you and what the sort of problem you're working on is. So that's a method of approximate mathematics. You're never going to get exact, but it doesn't matter because if your steps are small enough, you're guaranteed basically to get within as some tolerance of the actual local maximum. There's other questions though, which is if you did that, suppose that you had a mountain that looked like this, right? And you were trying to get to the top. If you follow the gradient, you could say, calculate where you're at and then go up in the steepest direction and calculate where you're at and go in the steepest direction. You could land on what's called a local maximum and not actually see the absolute maximum. So there's other stuff that goes into the mix when you're using these methods. But you should already see, if you're trying to find the maximum or minimum values of something, or the maximum values, this is a pretty easy way to geometrically do it, right? There's nothing fancy about this. It's just calculate a gradient vector. Computers are really good at calculating gradient vectors, it turns out. Okay, some other properties. It turns out that if I'm, okay, so this should be pretty easy. Oh, look, somebody brought me some visual aids here. Okay, so I'm standing, I'm gonna whack somebody with a stick. So I'm standing on a mountain and I calculate my gradient and there it is, right? There's my gradient vector right there. That's the steepest direction. How do I go down the mountain the fastest? I go like, well, remember, there's a tangent plane, right? I'm going to try not to kill anybody with this thing. Okay, so there's a tangent plane, which means if that's the steepest direction and I come around the plane, the opposite direction is going to be the direction of steepest descent. This would be easy if I had a plane here, right? You can see if this is a tangent plane to a surface and I put the gradient vector on it, that points in the direction of steepest descent and that points in the direction of steepest descent. And no matter how I orient it, that's going to be the same. So minus the gradient of f, so 3, minus the gradient of f is the direction of fastest or greatest decrease. For minus the magnitude of gradient of f is the slope, the rate of greatest decrease. Okay, another question. We got one more property. Suppose I'm tired and I don't want to climb and I'm scared. I don't want to go down, right? I just want to go around the mountain instead. There's the gradient vector right there. What direction should I go? Yeah, orthogonally, perpendicularly, 90 degrees, pi over 2 rads, whatever you want to say. Yeah, so if the gradient points in the greatest of greatest increase, and the negative gradient is the direction of greatest decrease, if I move perpendicularly to that, it should be the case that I don't go up or down, right? And so that means the gradient of f this is a really, I'm going to put this as like a mega powerful idea. The gradient of f is orthogonal to the level curves of f. So what I mean by that is, if I gave you a topographic map of a mountain, say, so there's the top of the mountain, and there's the next layer of altitudes, and there's the next layer of altitudes, and there's the next layer of altitudes. Maybe I'll make a little, yeah, whatever, that's fine. Okay. So these are places of constant height. So these are places where z is equal to c, constant height. And I would like to know how does water flow down this thing? This is an analogy. This is used in a lot of cases for other physical quantities. But just for now, imagine that's a map of a mountain. That's the highest point. That's the lowest point here, topographic map. And I want to know if I tripped and fell, how would I roll down? So the gradient actually tells me how to do that. Because these are places where if I travel on these curves, my height doesn't go up or down. The gradient must be orthogonal to that. So the gradient vector is going to point perpendicularly, and perpendicularly, and perpendicularly, and perpendicularly. So that is, at every point here, that's the direction of greatest increase. What's the fastest way up the mountain from that point right there? Follow the gradient, follow the gradient, follow the gradient, follow the gradient. So you get more than just how to do it. You can actually write paths down in terms of the level curves. Level curves determine a bunch of gradient vectors everywhere. And gradient vectors determine level curves. So there's this two-way relationship here. In fact, every point on this picture has a gradient vector attached to it because of that. These are all right angles. And that relationship is of profound importance for an optimization method called Lagrange multipliers, which we may or may not do, but it is one of the most commonly used numerical schemes for evaluating things. Involves the fact that gradient vectors and level curves are perpendicular to each other. That one, I can actually do all of this from the definition of the dot product. So we can prove all of this easily. This is not like a technical proof involving a definition. I'm going to ask you for a second to put on your 143 hats and tell me if I had the gradient of f dotted with the vector AB, so it's a vector u, what was the definition? Not the definition. There was a version of this that told us about the angle between two vectors. Look, so it was the cosine of two vectors. Do you remember the formula? The magnitude of the first vector, the magnitude of the gradient, times the magnitude of u times cosine of the angle between them. Okay, that's just the part of one of the properties of the dot product, right? The dot product has this property. So the size of this quantity, which is the directional derivative, this is the directional derivative in the direction u of f, that directional derivative is going to vary based on the angle between the vectors. When is it the largest? When is this directional derivative the biggest? When cosine, yeah, when the angle is 0. If the angle between two vectors is 0, what does that say? If the angle between two vectors is 0, then they're parallel, right? It's not perpendicular, but parallel. Cosine of theta would say that the vectors are parallel to each other. Cosine of 0 says the vectors are parallel. So the directional derivative is largest when the vectors are parallel. That's this. Is it possible for the directional derivative to be 0 when theta is? When it's what? 9. Well, okay. Pi over 2. So that's theta is equal to 0. 2 sticks. So that's theta is equal to 0, right? Remember, the directional derivative measures the derivative in all possible directions. So it's maximum when it points in the direction of the gradient because they're parallel to each other. It's equal to 0 when those vectors are perpendicular to each other. That's 0, which means the directional derivative is 0, which means there is no increase or decrease in that direction. When is it minimum? When the vectors are opposite from each other. Theta is equal to pi, which means they point in opposite directions. So theta is same direction, pi over 2 is orthogonal, pi is opposite directions. That's basically the assertion. That's points 1, 2, 3, and 4, and 5, actually, all of them. So this is basically a proof of all these properties. Think about the angles between them. The most sophisticated conceptual idea that I can say here is, and we'll see this later, what this actually means is, if you write me a function, z is equal to f of x and y, there's actually what's called a vector field attached to it. Every point in the plane will have a gradient vector attached to it. So one way of thinking about that is, if I gave you a function describing something like gravitational force, the gradient vector would tell you what direction the gravity is flowing, right? Or like the gravitational magnitude. Or If I gave you something about electric field, right? I told you the electric field in a piece of the plane. The gradient vector would tell you where the potential lines were. Right? Potential lines are in one direction and fields are in the other. So there's these vector quantities that tell you things about how things are actually flowing. All right. So I said all the stuff I want to talk about today. Let's see, geometric meaning of the gradient, and then just a bunch of cute exercises around computing these things and doing the geometric interpretations. What I want you to take away from the gradient discussion, is the gradient vector is easy to compute, but the important part of it is that it has all this geometric information inside of it. Okay? The geometry of the gradient vector is the thing that's important. I can climb my way up to the top of a mountain by following the gradient. Or I could climb my way down, or I could climb my way around. The gradient vector tells me how to do all of those things, and they're all used in practice a lot. All right? If there's no questions, we can wrap it up for the day. Questions on any of this? All right, so I'll see you in my office hours. Hopefully, I will be down there in the tent at, what is it? It's at, when did I say my office hours were today? 12 to 1? It's Tuesday. Did I say 12 to 1? 12 to 1. Then I will see you from 12 to 1.